In this lesson, we'll look at the bias variance trade-off for k-fold cross-validation. So there's some bias variance trade-off when we are using k-fold cross-validation. When with k less than n, k-fold cross-validation has a computational advantage over LOOCV. Also, a less obvious but potentially greater advantage is that it gives more accurate estimates of the test error rate than does LOOCV. This is due to the bias variance trade-off. LOOCV will give approximately unbiased estimates of the test error, since each training set has n-1 observations, which is almost the entire observation set. We saw that the validation set approach can lead to overestimates of the test error rate, since its training set is about half of the n observations usually. Doing k-fold cross-validation with k equals 5 or 10 will lead to an intermediate level of bias, since each validation set contains n over k observations and each training set contains n times k minus 1 over k observations. The size of the training set in k-fold cross-validation is smaller than in the LOOCV approach, but a lot more than in the validation set approach. Therefore, from a bias reduction view, LOOCV is preferred to k-fold cross-validation, but LOOCV has higher variance than does k-fold cross-validation. When we perform LOOCV, we are in effect averaging the outputs of n fitted models, each of which is trained on an almost identical set of observations. These outputs from LOOCV are highly positively correlated with each other. In contrast, when we perform k-fold cross-validation, we are averaging the outputs of k-fitted models that are somewhat less correlated with each other, since the overlap between the training sets in each model is smaller. Since the mean of highly correlated variables has higher variance than does the mean of many quantities that are not as highly correlated, the test error estimate resulting from LOOCV tends to have higher variance than does the test error estimate resulting from k-fold cross-validation. There is a bias variance trade-off associated with the choice of k and k-fold cross-validation. Typically, given these considerations, one performs k-fold cross-validation using k equals 5 or k equals 10, as these values for k have been shown empirically to yield test error rate estimates that suffer neither from excessive high bias nor from very high variance. We have studied the k-fold cross-validation approach in this lesson.